Right. So thank you very much for my patience. My first tip of the day is to never accept a meeting for just before your talk. I'm now going to demonstrate how to use a clicker. Yep, it works. Awesome. Excellent. Right, I'm going to take a deep breath. My name is Charles Bailey. I work at Bloomberg. I'm in developer experience. I try and help other teams and developers with their workflows, problems, issues, particularly when it comes to Git. I've occasionally contributed to Git. Still trying to get some sort of like a proper C commit to Git rather than just test scripts and shell scripts. But at the moment, yeah, shell scripts, that's where it's at. Hang on. Yeah, so today I'm going to talk about the index, which is kind of less understood than it should be. And I'll give you sort of a few ideas of how to work with it. You can take some of these ideas, try them out, see if they can kind of improve your workflow when working with Git. So, what is Git? Is anybody here not kind of vaguely familiar with Git at all? Has everybody done some sort of a Git clone at some point? Everybody awake? Yeah, most people are awake. Okay, cool. This talk does assume some knowledge of Git. So Git's a distributed version control system. It's like the model that's pretty much taken over the world now. Some people still use centralized systems like Subversion and CVS. Luckily, not so much CVS anymore. But the big advantage of a distributed system is that kind of all nodes in the tree of people working on the same repository are kind of equivalent. Everybody can make a commit at the node of their choice and communicate it in a safe manner with the other people they're working with. Most popular, obviously, in open source tools, but also used kind of commercially in kind of closed environments too. Attributes of Git. There are two kind of main ones that people talk about. Have I got? Yeah, no, I'm fine. Just wondering whether I'm getting shine from the projector or not. The first one, which is kind of quite remarkable for something that's so popular, is that it's hard to learn. And another attribute is that it has an index. And to my knowledge, no other source control system has an index in quite the same way that Git has. Bit of a mystery word, though. So interestingly, some people have kind of done research on this. And so I don't know if anybody's kind of heard of the tool called Gateless. It's a research project that these two guys kind of came up with when they were doing some research on software design. And in particular, they had some criticisms of Git and some suggestions for alternatives. And one of the things that they did is they came up with a new source control tool, which basically sits on top of Git, but gives supposedly, and they have some research to back this up, an easier to use interface. And one of the things that they did was they completely hid the index away. So it's no longer a user-facing artifact. And I found that very interesting. And also slightly disappointing because I really like the index and I use it and I feel it makes my life easier when I use it in the right way. Anyway, I recommend having a look at these papers if you're interested in this, and certainly you can have a look at Gateless. It's they don't claim it's a tool ready for production. It is very much a kind of exercise in here's how an alternative could be made. Cool. So I guess if I'm going to talk about it, it'd be good to know what it is. So. Just out of interest, who here would, hypothetically, feel comfortable, say, explaining to the person sitting next to them or the end of their row what the index is? Yeah, okay, yeah, 3 or 4, kind of, some not so sure. I hope to answer this question and perhaps in a way that will make you all feel comfortable doing that sort of thing. So I think to explain this, it's probably good to just have a quick review of Git's object model. Who here is familiar with Git's object model? Kind of more than would feel comfortable explaining the index, which is kind of what I suspected. So there are lots of good resources for this online. People have come up with diagrams, pictures. I've just got words because I'm quite lazy. There are basically 4 types of object in Git's object model. There's the blob, and what the blob represents is the contents of a file. It's not a file itself, it doesn't have a name, it's just a stream of binary data. Now that binary data could be text as well. Yeah, whenever I talk about this, I always think of text as a subset of binary. Some people think of them as alternates. Binary is just a stream of bytes. Some streams of bytes form text streams. So typically people manage text in Git. Some people store things that aren't text in Git. Depending on what exactly you're using, that can or can not be a good idea. So we've got a blob. It's just a stream of data. Then the next object is a tree. And a tree is kind of an analog of a directory. A tree is just a list of named, or it associates names with blobs. It doesn't, a blob can appear under different names, either in the same tree or in different trees. But we have name, also mode, so whether something's executable or not, and the contents. Mode also contains information about whether a blob is a real file or a symlink or a git link, but that's not important for this talk. So trees can also link not only to blobs but also to other trees, so you can have directory hierarchies represented. So you can So basically, when you check out a particular Git, that tree can be represented on the file system. The next object is a commit. And a commit is basically just a link to a tree with some metadata about the commit. So the author, the change message, and perhaps 1 or more, 0 or more parents. Perhaps 1 or more. That's the same as 0 or more, isn't it? Sorry, maybe I should insert some C++. Optional vector of, no. So a commit is just a reference to a single tree. And that's the complete tree that this commit holds. And a commit holds a snapshot, a complete tree. A commit itself doesn't directly define differences. You infer the differences that a commit introduces by looking at any parents that it has and comparing the tree of those parents with the tree in this commit. And that's kind of quite an important point. It's kind of quite easy to just kind of like totally miss that, because whenever we ask it to show us a commit, the default thing it does, it goes, it's a commit. Oh, and it has a parent. I'll show you a diff. Because typically that's what we want to see, and that's the kind of most useful thing. But fundamentally, a Git, just a commit, is just a link to a tree. And finally, there's a tag. And a tag can let you tag any other sort of Git object with some description. Most people tag commits. Some people tag blobs. Crazy people tag other tags. I've tagged a tree, but just to prove to myself it works. I don't know if there's any use behind that. Cool. Gosh, my slide says why. I still haven't answered the what. So what is the index? So the index is, at its simplest, a flat list of paths and the associated blob ID to that path. And the index is associated very much with a working tree. So if you've heard of a bare repository, one that has no working tree, it also has no index. Oh, and I don't know if you're familiar with the git worktree command. Git worktree allows you to associate a second, third working tree with the same Git repository. For each working tree, you get a new index. So it's very much one working tree, one index. It's not directly linked to your a repository necessarily. But the common case, single work tree for a repository, you have an index. So it links a name to a particular object ID, and if you're in a clean working tree state, that object ID is the actual ID of the file that you have in your working tree. But often as we're working and we're editing files, or if we've kind of removed some files or changed stuff, there may or may not be an actual file at that path, and it may or may not be up to date. So that object ID is only up to date when you've added that work tree to your index, or checked out from the index, done some operation to ensure they're the same. So why is it called the index? I think I may have answered that, so I'll just reiterate that. It's an index that maps a path name to a blob ID, and it's as simple as that. So does anybody know any other names for the index? Yes, cache. Stage. I like staging area, just because stage is what I'm not standing on, but yes. Staging area, and there's, that's a much more modern name. It's much more kind of popular. I think it's more friendly for new users, and I think it's generally a good name. But there are some caveats with the kind of mental model there. Cool, good. Yep, those are those ones. So a brief history of Git. Well, a snapshot of history in time. You can go back and check out the original Git version, and you'll be given this set of commands. And the interesting thing to note, so take this with a bit of a pinch of salt. Obviously, the first version for which there is a commit has some sort of a commit command. Otherwise, we wouldn't have that commit. So, you know, there'll have been versions where we've been hashing objects before Linus made the first commit that is still in the history. But one of the interesting things to note is that of the commands, 6 are predominantly to do with manipulating the index, or cache, pretty much as it was there. So we've got initdb, which is kind of not really, commit tree doesn't really touch the index. Cat file, I can't remember if in the original version it looked at the index, maybe not. So 5 or 6. The other 5 all strongly interact with the index. And many of these commands are kind of unchanged or barely changed in name. So cat file, commit tree, read tree, write tree, all exist in current Git. Initdb is just init now, although I think you can still use initdb. And update cache is now update index. I'm not quite sure what read cache is. I'm going to have a think about that. I think it might be just ls files now, or the closest equivalent. So obvious from here, the index was called the cache from a very early stage, and it was kind of core, even in the original version of Git. Oops, sorry, I really amplify when I do that, don't I? So similar to my discussion about commit, an index is a complete list of files. And again, this is something that you have to watch for, especially when you come to using the word staging area. A lot of the times when people say, so what changes have you got staged? They're just interested in, you know, differences. Whereas what's in the index or staging area is everything, including stuff that hasn't changed. It's a complete index. So when you do git status, you only see the stuff that's changed. But in the index, everything in the project, all the stuff that hasn't changed, is listed. Cool. Yeah, I'm on time. I'm back on time. What I'm going to do for the main body of this talk is just go through a few scenarios, a few tools that I've used, and a few points to watch for. Cool, so index tools. So bearing in mind the fact that the index is like a complete a list even of stuff that's not changed, does anybody know what the command to unstage something is? Or are there multiple commands? Does it depend on the scenario? Does anybody? It's not a trick question.
I usually reset.
Reset? Yeah? Yeah? Yeah. So interestingly, there's sometimes if you look at Git status and you're like, if you haven't made your initial commit yet, or the file's brand new, or stuff, people can go, oh, it depends what you're doing. But actually, reset pretty much works in every instance as an unstaged command. So if you've got a file in that you've just added, you haven't yet committed, sure, you can do git rm ---- cached, which is something you'd use to stage a deletion of a file, as, even if it was already cached. But if you're just looking to unstage, reset works in pretty much every scenario I know. Do tell me if I've missed something there. I did have a good poke around. The one thing that did surprise... Hello? Okay. Okay, yeah, fair enough. Yeah, I wasn't going to talk about submodules. I don't use them a lot. I have watched other people use them. There are a couple of scenarios where they're useful. Okay, yes, no, fair enough. Okay, I shall rephrase that. Reset works to unstage things in most scenarios where you've either stage and add, remove, or change in a single project without submodules. Cool. So one thing that's quite useful if you kind of want to understand the index is to be able to just list out what is in your index. I think I've mentioned it before. Is anybody familiar with that? ls files. And ls files minus s gives you a list of not only the paths but the ID and mode as well. So it's the closest representation to the user-facing aspect of the index. There's another one that's quite useful, and I'll come back to this at the end if you're interested in some of the more detailed working of the index, and that's --debug. So rewinding a little bit to the Gateless slide, one of the points that was made in their first paper is that for good software design, any kind of a user-visible, I forget the word they use, I'm just going to use artifact. Any user-visible artifact should have a single purpose that helps a user solve a particular problem. And one of the issues with Git's index is it has multiple roles. The user-facing role is typically to prepare my next commit, so to get everything organized so that when I commit, I have the thing that I want. But it also has an important performance role. So some version control tools give you a working tree where everything is basically read-only and ask you to make some sort of positive action to start editing a file. So I've used perforce before, which can operate in this mode. I don't know if it's the only mode it can operate in, but I certainly used it in an environment where it was in this mode. Certainly, RCS, which I've also used. Worryingly recently, in one instance, again, you CO minus L, you lock a file, and then you edit it, and then you can check it in. You shouldn't normally try and edit it before you've locked it. If you're not going to do that as a version control system, then you have to start, and then you're asked to perform some operation, such as make a commit or tell me what's changed. You're going to have to inspect the file system to see what's actually changed or what's actually ready. And that can vary in expense. And it depends on a number of things, like the number of directories you have and how many files in each directory, whether you've put your working tree on NFS or some other sort of slow file system. And so to make this as optimal as possible, what Git's index is it's also a cache of stat information. So this kind of brings me back to the other names for Git. And I'm not 100% sure, but I'm fairly sure that the caching of the stat information gave it its name of the cache. Although I also, we also use cache in other sort of mechanisms. So, I work on a file. It's a good enough state to kind of store away for the moment while I do some other stuff. So you might think I'm just caching that version of the file, which is kind of like a second meaning of cache. But my feeling is, just looking at the code, is that the caching of the stat information is where the name originally comes from. And what this enables Git to do is, if you ask whether a file has changed, if it's either written that file or read that file at some point because you wanted to add it to the index, what it does is it stores some stat information, so the file system metadata of the version that it knows on disk at that time match what was in the index. So last week, I reset hard, Git overwrote a changed file. Once it's finished writing that file, it stores the stat information in the index. This week, if I ask it what's changed, it can have a look at the stat information for that file and go, well, that matches what's in my in the index, so I know it hasn't changed. I don't need to read that file. I don't need to hash that file to determine that. And that's a big performance boost. And I actually have got not a live demonstration, but a recorded demonstration just to kind of show that later. Cool. She's there's water on my table. No. Okay. Oh, that's very kind. There is now water on my table. Yes?
The caching of the stat info, presumably that's just file modification, timestamps, and size.
No, it's not. I can answer that question later on.
Okay.
That's the majority of it, but there's other stuff too. Not much, but some pretty crucial other stuff. Cool, and yeah, do ask me anything at any point. There'll probably be time for questions at the end, but yeah, do ask me. I will get back to that towards the end. Cool. Okay, that's good. So my first of three scenarios that I happen to have done recently is moving stuff around between projects and also moving stuff from one project to another. Now, there are various ways you can do this. I mean, you can kind of like at a high level kind of pull the history of a second repository and kind of like merge it in and then do a kind of git move and stuff. But I've had a couple of scenarios where I just want to take I've had a demo repository that I haven't really taken much care on. I've hacked around, and suddenly now I've got a subdirectory of useful stuff that I actually want to bring into another repository. And you can do this kind of quite simply with some index commands. So why might you want to use this rather than the kind of git move stuff that I've talked about? Speed, it's kind of like faster for kind of big trees. Very occasionally I do something for another team and they want stuff shifted around and I don't care about their stuff and I don't even want to compile it and they've got this like whacking great huge directory. I can clone their Git repository and not check it out. I can do some manipulation and make a commit for them and push it to a pull request. And I don't need like those 100 megabytes of source on my file. And then it kind of goes off to our GitHub Enterprise install, some CI runs, get a green tick because I know I've got it right, and it's kind of really fast, and I'm back to my whatever I was interrupted from. So yeah, it's quite speed, saves space on my hard disk. The other thing is that you might want to do some manipulation as part of a filter branch. So is everybody familiar with a filter branch? No. Okay, so has anybody heard of the BFG tool for eliminating stuff from bad stuff from repository? No? Okay. Oh, yeah. Okay, a couple of people. So occasionally you need to do some serious history rewriting. And usually this is because somebody's got some done something bad at some point, and then you realize how bad it is later on. So, you know, they Git added their whole working tree for the initial commit, and it contained lots of object files and executables, and like half a year later somebody goes, no, really, I'm fed up, because with our CI now clones from clean every time, it's pulling down everything. Please make it stop. And that's kind of like, you can solve that in different ways with a shallow clone, but hey, who wants to do that? The other more serious instance is when your password file contains a real genuine password that you wrote onto disk for whatever reason and didn't mean to go in there. Then you kind of, yeah, you really need, you should rotate the password anyway, but you probably really want to expunge that from any record of history. So if you're doing some sort of big manipulation, and sometimes, you know, you want to pull out a subdirectory as a new project. And actually you can use subtree for this, but that's a contrib tool, so it's not always available. And if you want to do this as part of a script, you probably want it to be quite fast, automated. Filter branch has got a number of options. One of the options is it checks out the tree for you, runs a snippet that you provide to do some manipulations on that tree, and then takes that new tree as the new commit. And that's a little bit slow. In fact, it's quite a lot slow sometimes. If you can do your manipulation directly in terms of the index without needing a working tree, you can use another option to filter branch, which is an index filter, and it tends to be substantially faster. And when I say substantially, it depends on the cost of checking out each thing, but 10 to 20 times kind of easily. Cool. So one of the first things when you're doing manipulations is sometimes you want to clear the index. Just making sure I'm looking at, I've got the next slide and this slide, and sometimes I'm kind of like, I think you can see something that you can't. Yeah, one of the common operations is sometimes you want to start with a blank index and then use the kind of some subset of the existing tree and pull it into the index. And I'm ashamed to say I only found out this command kind of quite recently. So GetRetreive, it's kind of like the archaic version of reset, or if you've heard the difference between Git's plumbing and Git's porcelain commands, it's the plumbing behind reset, or at least one of the meanings of reset. Did I tell you about that paper about the design of Git? Yes, there are some other criticisms. So what readtree typically does is it takes a tree object from a Git repository, so it's in my object database, and populates the index with it. And for ages, I didn't know, readtree also takes a -- empty argument, and what that does is it just creates you an empty index. So it's like git rm -- cache -r, so recursively remove everything from the cache. But for some reason, it's a lot faster. I'm not quite sure why it's a lot faster. It's obviously a lot faster than if you're also removing stuff on disk, but it's just faster. So this one's quite useful. And the other thing I note on here is sometimes it's useful to make a second temporary index while you're fiddling with things, and then you may want to go back to the original index. And you can do this just by setting the environment variable git index file to something else. So yes, if you're writing scripts for filter branch, as a quick aside, do not assume that the index is .git/index, which is the normal. Maybe I should have put a slide with where is the index. So normally in a Git repository, the index is in .git and it's called index. But if you're running filter branch, normally you get a temporary index with a different name. And you can use the same trick in some scripts if you kind of want to do this sort of thing. Cool. So yes, I just mentioned this. If you want to populate an index with a particular tree, then GetRetreive will do this for you. It's like reset without options, except it won't move your head, if you follow what I'm saying. So, actually no, reset doesn't move your head, checkout moves your head, doesn't it? So it's low level, it doesn't look at any of your files on disk, it purely reads that tree into the index. And one of the things you might notice is that if you do use readtree to read something into the index and use readtree to then go back again, If you then do a get status, it can be quite slow. And what the issue is there is that it hasn't looked at anything on disk, so you've lost that stat cache. If you use -m, which only means merge, if you use it with a single tree, it'll try and keep the stat information up to date as much as possible, so that kind of problem is reduced a little bit. Obviously, if you move too far away and then back again, when you move far away and the object IDs are different, then it'll zero out the stat information because it knows that your objects used to match the old index. Your index now contains different objects, so obviously that stat information is no longer the stat information of something that matches the index. Cool. Yeah, I compared that with reset. Read tree always clears the index and reads a new tree into it, except if you use ---- prefix. So this is kind of quite useful for kind of bringing things into a subdirectory. Important thing is you... Right, everybody's awake again, great. So do you want me to repeat the last slide? The important thing to remember here is please remember the slash. The documentation says you shall have a slash at the end. Does seem to work without the slash, and it does the, well, if you're thinking in the right bizarre way, it does the expected thing of check everything else out with a prefix instead of like as a subdirectory. So yes, is that a good idea? So if you put a prefix of capital A, you'll have a like a.getignore or something like that. So it's not documented to work like that. It kind of obviously does. One interesting thing is like if you leave off the prefix entirely or just put it as a single slash, then it's like read tree without any argument, except the important side effect of it doesn't clear the existing index. So you can actually kind of merge multiple trees in at the root level with read tree. But it's not a true merge because it'll just replace, I believe it replaces stuff. So normally you'd only want to do this if you know you've already get kind of subdirectories that aren't going to conflict. Cool. So with ---- prefix, I can merge in things as a subdirectory, or I can bring two trees together. So obviously with prefix, I can move things down a level. So I think I have actually already hinted at this. What if I had a subdirectory and I wanted to pull it up to the top level? Supposing I had, in my repository, there was always a documentation folder. I wanted to create a new repository which just starts with the contents of documentation. Any ideas how that one might be done? It's what, a prefix of .. I don't believe that will work, but I haven't tried it. It's an interesting thing. You certainly shouldn't be able to put anything outside of the repository root. So the hint is like read tree takes a tree-ish. So you don't have to provide a commit to read tree, which would automatically be dereferenced into the root tree. You can actually pull out a subdirectory. So if I did, for example, if I wanted the tree ID of a documentation folder, I could do head:\documentation, and then I have the ID of the tree subdirectory in the documentation folder. And if I pass that to read tree, I'll get a new index which just contains everything that was in documentation, kind of at the top level. Cool. So that's kind of moving stuff around. One scenario that I used this relatively recently is a team I knew had kind of decided to split out their repositories so that we could have a library per repository, which sounded like a good idea because like, you can kind of build them separately, you don't conflict when you're changing the same thing. However, in practice, all the libraries were released together. Lots of stuff was, I won't call it tightly coupled, but reasonably coupled. So they had a lot of changes which spanned repositories. And they were having a lot of pain with this. And they decided that actually they'd made a mistake, and what they really wanted is everything back into, I don't like to use the word monorepo, but that's pretty much what it was for their set of libraries. By using, so on the individual repositories, I can create a new repository. I can fetch from all the other repositories just so I've got the commits available. And then I can just use GetRetreive with prefix to pull them all into separate libraries and just make a single commit. And what I actually did was I created a big octopus merge for them that brought them all together, retained the histories, but had them all now in separate subdirections of the same repository. They found the new monorepo infinitely better to work with. Cool. So losing bits of my clicker. Not my clicker, obviously. So ignoring stuff. So there are a couple of scenarios where you have stuff in tree that at various points in the development process you don't want to be normally included in a sort of commit action or a reset action. So one of the things that people often do is they have some sort of a config file, maybe there's a connection to a service, maybe there's a URL, maybe there's some credentials. And a lot of people do this in various ways. I have my preferences, but a lot of the time they'll put in some sample stuff and comment it out will be password, and it says, modify and put your password here, and then you can kind of test on your client machine. And that's kind of a little bit annoying because it's like you want that file in source control, but generally people are going to edit it individually, and maybe it's going to be kind of different when you deploy. It's kind of nice to have a better configuration management, but for better or worse, especially when people are starting a new project, it often kind of tends to be like this. And historically, the tool for this was assume unchanged. And that was slightly unfortunate because assume unchanged really had a different purpose. Assume unchanged, the original kind of purpose and motivating example was like, I've got a really big tree and I'm only working in a small part of it, so actually I don't want Git when I'm kind of like, asking it what's changed or stuff, just descending into all these other places that I don't really care about. And so, this flag was kind of used, and the recommendation was you can just set this flag on tons of stuff, and then Git will just literally assume it's unchanged. And that kind of, so for the config file scenario I was talking about, that kind of works, because when you edit the file and put your own password in, or some test URL, or whatever it is that's different that shouldn't be checked in. If you did a commit -a or a git add -u, or whatever your favorite way of just like adding everything in the tree was, whenever Git came to look at your config file, it would see the assume unchanged bit and go, I'll assume the one on disk is the same as the one in the index, and I'll just use that instead. So you'd never get your personal version added to the repository. Unfortunately, it also works the other way around. So if you were to pull, merge, rebase, check out a new commit basically that had an updated version of that file, when Git came to check out all of the changed files that you don't have that are correct, it would go through and it would find this config file and it would say, assume it's unchanged on disk. So, this file hasn't changed, but there's a new version, and just flat out overwrite it, even though you might have put some kind of like important stuff in there. So that's kind of not ideal. So the better thing to use is, for this scenario, is the skip worktree bit. And this pretty much works in a very similar way. The difference is Git will never touch the worktree for this file. I mean, it's pretty much what it says. So in this scenario, it just never reads or writes the file kind of at all until you remove the work tree, skip work tree bit if you actually wanted to kind of do some changes to it. I kind of prefer not having that sort of config file directly in source control. My general recommendation is if you have some config that is kind of global for all developers, the project, have that in a config file, and then try and have a file that can overwrite it, so a config.local or something that people can create. And what you might want to do is have something like a config.local.template or something that people can copy from and modify, and then put the path that people are supposed to create and manage themselves, just put that into the .gitignore in tree in the repository. And that tends to be much cleaner and much less overhead for all your developers than using something like the skip work tree bit. Cool. Any questions on that, the differences? Yes?
So this command modifies the entry and index for a particular file.
Yes.
So for this file, skip work tree.
Yes.
And that only affects my machine?
Yeah, so I should have put a path on the end of this file, so you can put multiple paths. It's an index bit, so like assume unchanged, it's stored in the index, so it's directly related to the working tree and its associated index that you're running this command for. So yes.
So remove these options, you just do update index with no.
Yeah, both of those two have got a no dash. Skip work, no skip work tree or no assume unchanged, which is not assume changed. From the keynote, we'll know about our double negatives. Maybe we should have a minus maybe changed, perhaps. Cool. So one of the problems with skip work tree, though, is that, as I said, it's set on the index, and it's also therefore associated with a file path. So typically what you might do is you might go, oh, there's this big mono repo of the kind that I've described before, and I'm only interested in lib1, so I'll just kind of like Gateless files, grep everything that isn't lib1, and pass that to like xarg skip work tree. So there's another kind of reasonably common thing. So what happens sometimes later is somebody adds some new files to lib29. Of course, because the skip work tree is associated with particular paths, because it's a flat list of paths, it doesn't contain trees like a commit, those new paths won't have skip work tree bit set. So now you'll have lib1 and like new stuff added to lib29 just out of the way, which is definitely not ideal and pretty much totally unexpected for most people. So there's actually another feature of Git, which is sparse checkout. Has anybody used sparse checkout? No, I'm putting my hand down too. I haven't really used it in anger. No, I have used it a bit. I use it in preparing my slides. So it does actually work. So if you set the core sparse checkout config option for a repository, just thinking, so this will apply to all work trees if you have multiple work trees in a repository. There's something I didn't try out. You give up the right to manage your own skip work tree bits, which is probably a good thing because, as I've described, it's a pretty manual process and it goes wrong. And instead, what you can do is you can put in patterns into the sparse checkout file. And this is the same sort of patterns as you may use or see in gitignore file. And what this says is only things that match this do I really want to be checked out. And then once you've enabled this Boolean and added this stuff to your config, Git will start managing the skip work tree bit for you. So every time you move to a new commit that's got some new paths that are not in your sparse checkout, they'll be marked skip work tree automatically without any need to do that yourself. If you try and manually change the skip work tree bit, those changes will probably be lost when Git does some tree operation that affects those paths. So it's kind of important if you're kind of doing sparse checkout that you don't you don't feel, you don't expect to be able to do any manual skip work tree bits. Yes?
If I accidentally delete one of those files from the working tree, can I get them back then, or do I have to remove them first from the sparse checkout also?
Sorry, so what's the...
So like I add a file to the sparse checkout, and now I accidentally delete it from the working copy. Can I restore it again? Can Git get it back for me?
So when you say you add it, so the sparse checkout is like a positive file. It's a list of things you do want to check out.
Right. So I have some files that are filled out by the
Right.
sparse
Yep.
checkout. I don't want I want the index to ignore them basically. Right?
Yeah.
That's what it says. But now I accidentally delete one of those files from the file system, and now I basically want to do a Git checkout to get that file back.
Mm-hmm.
Can I do that?
So typically, when you do a sparse checkout, it's generally because you're about to kind of remove all of these from on disk, because at the point you add them to sparse checkout, so if you cloned without the checkout option first and then set out your sparse checkout, and then you did reset hard head or a git checkout dot, then you'll only get the stuff that's included in the checkout stuff. So if you wanted to, it is true that if you just added those paths after you have an initial, everything would basically be frozen in time from whatever state you were at. If you wanted Git to kind of like be able to restore something, you'd have to specify, you'd have to add it to your sparse checkout list as an explicit path to get that version back out. But typically you add something to a sparse checkout because you want to actually remove everything that isn't there from your working tree because it's too big, it's in the way. It's not being kept up to date anyway. I think there's a... If you look at read tree, there is an explicit option where it can ignore sparse checkout. Yeah. You can ask me anything, I won't necessarily have the answer. Cool. So yes, potentially useful in monorepos, but to me it's a bit of a smell that actually at this point you probably could split up the repository. So the team that I was working with did actually have kind of builds that could happen separately. And if you've got some sort of top-level build thing that goes into everything, then sparse checkout is probably going to not work out for you. And if sparse checkout does work out, it's almost like stuff could live in different repositories at that point without as much penalty. Cool. What time did I guess I was a little bit late, so I started after 2. We're 3 to 3:30, aren't we? Yes, awesome. We're on time. It so surprised me. I couldn't believe it. Awesome. So performance considerations. So this is actually going back to a question I was asked earlier about what is in the stack cache. What is in the stack cache is actually, as well as modification time, mode, file size, and creation time, it also stores the device number and inode number, if applicable on your operating system. I don't know what it does on Windows. No, I do know what it does in Windows in some scenarios. So what that means is, if you were to say rsync a Git repository with its .git directory from one place to another with the archive flag, so you're preserving as many details as you think you can, you've still got brand new inodes. Probably the device is the same unless you've kind of synced it onto a different file system, but you have brand new inodes. So the stat information no longer matches. And if you do a performance comparison of something simple, like supposing you had a clean tree and you just did git status, and maybe you redirect the output to dev null just for, just to keep it quiet, you'll find there's a significant performance difference. The one that was the source of the rsync operation will be really fast, and the one that was the target will only just be fast. However, you do it second time, it'll be really fast, because the operation of running git status, it will have to inspect the stuff where the stat cache doesn't matter, and if it finds that although the stat information didn't match, the file hadn't changed, it will update the index. Does that answer your question about the?
To a degree, but
Yeah, okay.
I was actually thinking more the inverse, where if you had a file and you spoofed the modification time to be back to what it was, and the size had stayed the same, but the content had changed, would it then mean that it wasn't detecting the change?
So you'd have to. Yes, you can trick it.
Yeah.
It would have to be, yeah, it would have to be the same inode, so you couldn't kind of like, you'd have to be careful if you wanted to kind of like, some of the in-place sed commands would probably kind of like write a new one. So, yeah, it's possible to fool it.
Okay.
But yeah, it has to be a deliberate act.
Fair enough.
So here's a demonstration of, I cloned the Git repository because I just love write recursive stuff, and it's kind of when I want a reasonable size stuff, so something that's not as big as the Linux kernel, but still pretty big. There's quite a lot of history. Often use the Git repository. So I cloned the Git repository. It's at some version like 2.13 release candidate, or is 2.13 out? I don't know. If you do a git read tree head, what it will do is it will read the tip commit, the tree at the tip commit into the index, which is kind of like a no-op, because I had a clean checkout. But you'll see here, like I have a confession to make. This was run on Ubuntu on the Linux for Windows subsystem. I wanted to have something with, a bit of performance issues on my new Surface Pro that I'm playing with, and it took about 2 seconds of real time. And then if you run git diff again, it takes like 0.1 second. Because once you run git diff, like many commands, if it finds that the stat cache is not up to date, but there are no changes to the file, it updates the stat cache. And it matters. It makes a huge difference. That's, nearly 16 to 20 times faster-ish, roughly, hand-wavy. I ran these a few times, and the particular times didn't change very much. I'd done it a few times even before I got the 2-second response, so everything was reasonably kind of hot from an operating system cache point of view. The command, so lots of porcelain commands kind of update the stat information. If you're doing some scripting and you want to do it kind of explicitly, the command is git update index refresh. The slightly weird thing about this, and I don't know if it's this particular version of Git, I haven't really investigated, is if you add up the times that I took to explicitly refresh the index and then do a diff, it still adds up to way less time than just doing the diff that had to update the stat cache. And this was fairly repeatable as well. I tried it a few times and then went back to doing just the git diff itself. Git diff is, if your stat cache is not up to date, is always less efficient than doing an explicit refresh index in a git diff. There's probably a patch in there somewhere, isn't there? There's some optimization that could be done. Cool. So here's my demonstration of the -m flag. So what the -m flag does is, if you read a tree into the index, if any file, blob, path, and contents hasn't changed between what was in your index previously and what you're putting in your index, and the stat information was up to date, so your working tree is clean basically, it will copy that stat information. So this takes read tree a little bit longer because it's looking at the old index and copying some stuff across, but not. I mean, it's not noticeable. The read tree itself is an incredibly fast operation. It wasn't even worth timing it. And then git diff again is kind of really fast. So yeah, that's kind of just recapping what I've just demonstrated, I think. Cool. Yeah, what might invalidate the stat information? As I mentioned before, like an rsync would. You touch the files, all of the things you'd kind of expect to. Most of the user-level commands from Git preserve the stat information if they're not actually changing a file on disk, even if they're doing other stuff. Backup and restore. And normally it's just not an issue because the first kind of user level command will fix everything. There are some gotchas for scripts. If you're using diff files instead of diff as a kind of a low-level thing, what you sometimes notice is if the stat cache isn't up to date, it might print that a file has changed, and then if you're using an option that says, and what are the changes, there'll be an empty set of changes, which is kind of possibly not what you're expecting. Forgotten how to sort of stuff behind there. Cool. So I guess it's time for kind of a quick story. Had an incident where we had a program that was indexing over a lot of checked out Git repositories, and it was doing some incremental indexing. So it was doing indexing by kind of keyword and symbol over tons and tons of source files. We moved from a really kind of old way of doing this to a kind of more up-to-date version where we kind of keep repositories checked out. I can't exactly remember what it was doing before. We were keeping some repositories checked out and doing a fetch, resetting hard to the default branch because we had to allow for people who might rewind their default branch. Kind of not recommended, but some people do, so we didn't want any kind of merges to be happening in our automated script. And it turns out the new way of doing things was like much slower than people expected. It was taking forever, and we asked the guys in charge of the search facility, so you know, what's up? Our Git process seems to be kind of like fine. It seems to be kind of checking stuff out. And they said, well, no, Git's rubbish. It's updating the timestamp even for stuff that hasn't changed. It's because you're using reset instead of like merge, which was like fine for us, and we only sometimes had to manually go in and fix stuff when people had done stuff. And I was going, nah, that's not right, because I know Git. It's written reasonably well. If stuff hasn't changed, it doesn't touch it on disk. After a while of debugging, it turned out that they were using our script to update stuff. But overnight, they'd kind of like, for safety, take a copy of all of the Git repositories into a second area. Except what they would do is they would move the entire file system tree somewhere else, and then rsync it back to where it was originally. So when it came to do the Git reset, we were just doing a Git fetch, and then we're doing a reset ---- hard. Git will look at the index, and it will look at the cache stat information, and then it will see if it needs to actually replace stuff on disk. But it doesn't bother to go and look and see if the files change. So if the stat information is not up to date, rather than going, oh, well, I'll read on disk to see if it has changed, and then because I'm doing a reset hard, just write over it if it has changed. If the stat information isn't up to date, it just writes it anyway, because you just asked it to overwrite the file. So there's no point if the stat information is telling it might have changed, there's no point to reading it to see if it's actually changed, because all it's going to do is write over it anyway. So it's not, there's no benefit, well, almost no benefit to it actually reading stuff if it's just going to overwrite it anyway. Once we found out what the actual process was, we added a Git update index refresh, and suddenly indexing was cheap again. And I've lived happily ever after since. Covered a bit about the index, some of the ways you can manipulate it, hopefully do I have that? Oh, yes. So yeah, the index, it's kind of core to Git. It's kind of central to the way it works. It's been there since the start. It's very, very important to Git's performance. Lots of operations would be annoyingly slow. So another one is, of course, Git grep, which is very, very fast, often faster than a recursive grep. Some people have told me about tools that are even faster for that sort of stuff, but I haven't investigated them. Without the index, it would be kind of as slow as grep -r. And understanding it and being able to manipulate it is kind of useful in a number of scenarios. And hope you'll be able to kind of take away some of the stuff that I've talked about, maybe have a play with it, learn how the stuff works, and then maybe if you'll kind of end up in scenarios like I find myself, use some of the stuff to improve the way you do things. So thank you for your attention. I think I've got plenty of time for questions.